So we've been talking about graphs and problems on graphs. We started with reachability and then we talked about very complicated problems like graph coloring and vertex cover and so on. So now let's get back to reachability and connectivity and ask a more fundamental question, which is how do we actually work with these graphs in a mathematical setting? So remember that a graph consists of two sets, rather a set and a relation, a set of vertices and an edge relation. And let's focus on reachability back for now. So a path in a graph is a sequence of connected edges, and we say that V is reachable from U if there is a path from U to V. So as humans, if we see a graph like this, then what we will do is take this picture and stare at it and extract this graph in some sense visually, right? So we will take a graph like this, and so you can maybe by trial and error, but by exploration we will do this. So we can see that there is a path from V9 to V0. The problem is that we want to operate on this mathematically. We don't want to have this picture because there is no way to formally represent this picture and how you operate on this picture in terms of a procedure that we can execute, right? So how do we represent this picture in a way that we can compute reachability, for example? So first we need to represent this graph in a way which is more amenable to computation than a picture like the one on the right. So one way is to use what is called an adjacency matrix. So let's assume that the set of vertices consists of n vertices, right? So this is the normal convention in graph theory that we always use small n to represent the number of vertices, and small m very often is used to represent the number of edges, okay? So in particular, if we say that the vertices are n in number, then we will usually, just for simplicity, number them and call them 0 to n minus 1. You can also call them 1 to n, but in computing it's very common to start numbering at 0, so we'll call it 0 to n minus 1. And of course, when we actually have real vertices like names of cities, like in this case Delhi and Madurai and all that, then we will actually use some kind of a table to map the actual vertex names to this set. So for instance, we might have a table which says that Delhi is V0 and Madurai is V9 and so on. So Delhi is 0, Madurai is 9 and so on, right? So in this representation, where vertices are now numbers between 0 and n minus 1, an edge is a pair of numbers, right? So an edge is a pair I comma j, where I and j lie in the range 0 to n minus 1. And we usually assume that we don't have edges like this, right? We don't have the so-called self loop, so we don't have an edge from I to I. So we usually assume that I is not equal to j. So when we have an edge I comma j, they both are in the range 0 to n minus 1 because that is our set of vertices, but I is not equal to j. So given this, we now have what's called an adjacency matrix, right? In adjacency matrix, we have rows and columns numbered from 0 to n minus 1, right? And then you put an entry in this matrix 1 if there is an edge from I to j, otherwise it's 0, right? So the default is 0 and you put an 1 wherever there is an edge. So if we look at this graph on the right, here is the corresponding adjacency matrix, right? So first of all, because we have 10 vertices numbered 0 to 9, we have 10 rows and 10 columns, and the headers in red and the column headers and the row names on the left are in red, indicating that this is row I and column j. So now we take an edge, say for example, we take an edge from 8 to 5, right? So 8 to 5 says that the row 8 and the row column 5 must be a 1. So if I look at row 8 and I look at column 5, right, then I get a 1 at this position. So that's how I fill entries in this matrix, okay? So you can check that this matrix represents all the edges in the graph. So if you take any edge in this graph, so if you go here for instance and you look at this graph and you say, okay, 0 is connected to 1 and 4, well indeed 0 is connected to 1 and to 4, right? And because the edge, this bidirectional edge between 0 and 4 is actually two edges, as we said, so this is not an undirected graph, it's a directed graph. So in this directed graph, we are just using a shortcut to represent the two edges by putting an arrow at both ends, but actually there is a separate edge from 4 to 0, right? So there is an edge from 0 to 4 and there is an edge from 4 to 0, whereas there is an edge from 0 to 1, but there is no corresponding edge here from 1 to 0 because there is no backward edge on that route, right? So this is the adjacency matrix for this directed graph. Now we can take the same airline route matrix, and supposing we assume that all the routes are actually bidirectional. That is, whenever the airline flies from one city to another, it also flies back. So then we don't need to record these edges anymore, and then it's better, as we said, to take such a graph where the edges are all symmetric and explicitly call it an undirected graph rather than recording arrows in both directions. So we will draw it in this fashion, where we just draw an edge as a line connecting these two vertices with no arrows. And now if we look at this graph, every time there is an edge from I to j, there must necessarily be an edge from j to I, because it's a symmetric edge relation. And if you look at the matrix, then if you go across down this main diagonal, right, and then if you look at any entry like this entry here, then if you look at the symmetric entry on the other side, it must be the same, right? If there's an edge from 6 to 3, there must be an edge from 3 to 6. Similarly, if there's an edge from 2 to 1, there must be an edge from 1 to 2, right? So this is now our thing. If there's an edge from 0 to 4, there must be an edge, 4 to 0, there must be an edge from 0 to 4. So an adjacency matrix is very simple, right? So you just create a row and a column for every node in your graph, and then at the intersection of the corresponding row and a column, if there is no edge, you put a 0. If there is an edge, you put a 1. That's all there is to it. So now we want to compute with this matrix. So the whole purpose of doing this is now that this matrix on the right, for instance, is supposed to represent, right, the same picture as this undirected graph. So we have thrown away the picture and now we are looking at only the matrix. So in this, if you look at the undirected graph, for instance, then if I want to know the neighbors of I, that is, which are the vertices to which I is connected by an edge, right? Then I go to the row. For example, I'm looking at neighbors of 6. I go to the row where 6 is the starting point, and then I find that there is a 1 entry in column 3 and column 5. So this says that the neighbors of 6 are 3 and 5, which if you go up is indeed the case. The neighbors of 6 are 3 and 5, right? So without looking at the picture, I can just, in some sense, mechanically analyze this table or this matrix and get the same information that I would get by looking at the picture. And this is what we need, because there is no way that we can actually design a computational procedure which looks at the picture and then makes decisions based on the picture. So if you have a directed graph, it's slightly more complicated, because in a directed graph, remember that we have outgoing edges and incoming edges. So the notion of a neighbor is slightly more complex, right? So we have rows which represent outgoing edges. So if I take the row for 6, right? So the row for 6 has an entry pointing to 5. So now we are looking at this picture. So we have an entry pointing to 5 because there's an edge from 6 to 5, but the edge from 3 is coming in. It's not an outgoing edge, right? So if we look at this graph for the directed case, then we have to look at the column for 6. We have to say which things end in 6, right? So the column for 6 has an entry in row 3. So there's an edge from 3 to 6. So the rows represent outgoing edges and the columns represent incoming edges. Now in an undirected graph, these are symmetric. If I have an outgoing edge to j, then I must have an incoming edge from j. So both of these will have the same information. So actually I can also find the neighbors of a vertex in an undirected graph by looking at the column I. It's conventional to look at the row I, but the column I has the same information. But in a directed graph, this is different. The outgoing edges are in the row, the incoming edges are on the column. So the number of neighbors has a name in graph theory. This is called a degree, right? So the degree of a vertex is the number of edges which are incident on that vertex. That is, number of edges which start from that vertex in an undirected sense, right? So here, for instance, we saw that the degree of 6 is 2, because if I look at the row for 6 or if I look at the column for 6, right? So if I look at the column for 6 also, I find that there are 2 incoming edges, as so to speak, from 3 to 5, 3 and 5, and there are 2 outgoing edges from 6 to 3 and 5. This is undirected, so there is a uniform notion of degree. Whether you're counting edges as coming in or going out, it doesn't matter, right? So the degree of a vertex is the number of edges, and notice that each edge must go to a different vertex. So if you count the vertex you're starting at, there are n-1 other vertices. So the degree could be 0, in which case this vertex is not connected to anybody. I'm a friendless soul, for example, right? Or I'm in a city which is not served by this airline. So I don't have any edges. So I could have degree 0. Or I could at most have degree n-1. Everybody in the class is my friend, right? So I am one person and all the n-1 other people are my friend. So I have degree n-1. Or I have a direct flight to every other city on the network. So this is the case. So the degree is between 0 and, okay, so 0 less than equal to degree is less than or equal to n minus 1. So this is something that you should remember. Now, if I have a directed graph, this notion of degree now gets split because I have incoming edges and outgoing edges. So typically one talks of the in degree and the out degree. So the degree of 6 in the undirected setting was 2 because there were 2 edges, but actually one was pointing out to 5 and one was pointing in from 3. So we can say that the in degree is 1 and the out degree is 1. So our goal, as we said, was to compute, right? So we want to do something with this graph. So in this particular case, how can I use this adjacency matrix to check whether Delhi, which is the vertex 0, is reachable from Madurai, which is the vertex 9. So we do the natural thing, which is we start at 9 and then we see where all we can go, right? So we first mark that from 9 we can go to 9. So by marking, what I mean is I will now take the row entry and I will change the color from red to blue. So 9 is now reachable. So now I can look at the neighbors of 9. In this particular case, is only one neighbor, 8, right? And if 9 is reachable and I can fly from 9 to 8, then 8 is also reachable. So I would mark 8 as reachable. Now what do I do? I have to start from 8 and see where all I can go. So I just have to systematically repeat this procedure, right? So I have to systematically mark all the neighbors of marked vertices. So 8 was marked. So now 8 has 3 neighbors, 5, 7 and 9. Now notice that I don't have to refer to the picture. I'm only referring to the table. I just have to look at the row for 8. And if I look at the row for 8, I know what the neighbors of 8 are. Right? So I don't have to go back to the picture and imagine anything. This is just a mechanical analysis of this table. So I look at this and this tells me that I must now mark 5, right? I must mark 7 and I must mark 9, but 9 is already marked, so it won't have any effect, right? So the next step is to mark these new guys as also being visited or reachable. So I mark 5, 7 and 9 as also reachable. So now I have from 9 I can reach 5, 7 and 8 other than 9 itself. So now I've not been very careful to keep track of it, but I know that I've explored the neighbors of 8, but I've now discovered 2 new neighbors which I could reach, 5 and 7. So I pick one of them, say I pick 5. So I look at the neighbors of 5, right? So 5 has as its neighbors 3, 6, 7 and 8, right? So I have to now mark 3, 6, 7 and 8, of which 7 and 8 are already known, right? So I would mark 3 and 6. Now once again, I have now as unexplored things, I had marked 7, but I have not looked at the neighbors of 7. I have marked now 3 and not looked at it, and I'm not, so 5, 8 and 9 have been explored. That is, I marked them and then I also marked their neighbors, right? So let me again go to the smallest unmarked thing, so 3. So I look at 3 and I look at its neighbors. So the neighbors of 3 are 4, 5 and 6. So this means I must mark 4, 5 and 6, of which 5 and 6 were already marked before, so nothing happens, but 4 gets marked. And now the smallest unexplored vertex is 4, so I look at the outgoing neighbors of 4 and I get 0, 3 and 7, and therefore I must mark 0, 3 and 7, right? And so once I mark 0, 3 and 7, I can stop because this was my target, right? My target was to find out whether 0 is reachable from 9. And what I've seen is by systematically marking everything which is reachable in 1 step and 2 steps and so on, I have found out a way of reaching 0 from 9, right? So I may or may not be able to reach 1 and 2. I don't need to do it for this particular calculation. If I wanted to find out what all is reachable from 9, I would continue and see if 1 and 2 get marked. But in this particular case, my only goal was to find out whether 0 is reachable from 9, I can stop, right? So the other situation is that it is perhaps not possible to reach 0 from 9. And what will happen there is that after I mark everything that can be marked, I will find that 0 is still not marked, right? So if at the end of this process where I have marked all the vertices and all the neighbors of all the vertices and I cannot mark anything more, and I find that some vertex remains unmarked, then that vertex is not reachable from where I started. So abstractly what we said is we mark the starting vertex or the source vertex as reachable, then we systematically mark neighbors of marked vertices and we stop when the target becomes marked. So this is what we computed, and we did this using the matrix. That was the important thing, that we did not go back to the picture and try to follow edges on the graph as a picture, but rather we scanned the rows and we did some recoloring of the row headers, and in this process we were able to explicitly compute whether we could reach 0 from 9 or not. So we had a kind of ad hoc strategy which said that, we will mark some things and then we will pick up the smallest thing we have not explored and all that, but we didn't systematically tell how to do that. So we actually need to elaborate that strategy more carefully in order to get an actual computational procedure out of this. So how do you systematically explore the marked neighbors? So it turns out that there are two broad strategies for this. So one is called breadth first, which is what we were doing in a sense, but not really, which is that you propagate the marks in layers, right? So we look at things which are reachable in one step, and then from one step we look at things reachable in 2 steps, and so on. And the other strategy is called depth first, which is I find one place I can go to. There may be 3 places I can go to, but instead of going to the second place, I go to the place I could go to first, and from there I start exploring further where I can go, right? So then I keep going down that path, and then eventually I hit a dead end saying that there's no more places I can reach, and then I go back and I say, okay, now let me pick up the second place I could have started with and see where all I can go from there. So this is called depth first search. So you basically go as far as you can go in one direction, then you back up, and then you take the second direction, back up until you run out of directions to do, right? And you keep doing this at every point, and this is called depth first search. So we will study breadth first and depth first search in more detail as we go along. But before we do that, let's get back to this notion of how to represent a graph. So the strategy that we have seen so far is to use this adjacency matrix. So the problem with the adjacency matrix is that, as we have seen before, if you look at the adjacency matrix here, you will see that there's a large number of zeros, and zeros convey no information to us. It's only the ones which are useful to us, right? So the number of ones is relatively small compared to the number of zeros. So zeros are non-edges and ones are edges, and we are really interested only in the edges. So the size of this adjacency matrix, if I have n vertices, is going to be n squared regardless of how many edges I actually have, right? And now this is not a real problem in the long run or in the extreme case, because you could have about n squared edges. So if you have an undirected graph, right, then every pair of vertices will actually be an edge, right? So you will have, in terms of undirected edges, you will have n into n minus 1 by 2, because every edge is counted twice. But if you look at the matrix, it will actually have n into n minus 1 entries, because ij will be in the entry and ji will also be in the entry, right? So ij and ji represent the same edge, so the number of actual edges is half that, right? But the number of entries is going to be n into n minus 1, and of course if it's a directed graph, also you have n into n minus 1, so it should not be by 2, right? So in both cases you could have about n squared edges, but typically you will not have n squared, right? So typically a graph will have much fewer than n squared entries. And if you have much fewer than n squared entries, then it's not clear that having this large matrix is the best way to represent a graph. So the other option is to just directly represent the neighbors of each matrix, of each vertex in a list. So this is what is called an adjacency list, right? So in an adjacency list, what you do is you just write down for each vertex which are the neighbors of that vertex. So it's most sensible in a directed graph. So let's look at this directed graph here. So it says that 0 is connected to 1 and 4. So again 0, you put this list 1, 4. Similarly, 5 is connected to 3 and 7. So against 5 you put 3 and 7, right? So for each vertex in your graph, you just record what would have been in the adjacency matrix, what would have been the ones in the row for that vertex. So if you look at row 5 in the adjacency matrix for this directed graph, it will have 2 ones at 3 and at 7. So instead of writing all the zeros on the other 8 positions, you just write the 1 positions as 3 and 7, right? So this is an adjacency list. So this is an alternative way of presenting a graph, okay? And we can work with this representation as well. So on the right hand side, you see now the 2 representations for that particular graph we have been looking at. The top is the adjacency matrix for that directed airline graph, and the bottom is the adjacency list for the directed airline graph. And it's obvious from this picture that the adjacency list is typically much more compact in terms of the amount of space that it occupies. But of course, you have to do different things when you compute with these 2 things. So for instance, if I want to check whether a vertex j is a neighbor of vertex I, is there an edge from I to j? In the adjacency matrix, I just have to look at the cell I comma j and check whether it's 1 or not, right? So assuming that I can look up every entry in the matrix in constant time, right, in the same amount of time, then checking whether there's an edge between I and j takes the same amount of time for every I and every j. On the other hand, if I want to check in the adjacency list representation whether, say for example, there's an edge from 8 to 9, then I have to go to 8 and then I have to walk down this list, right? In this case, I have to first check that the first entry is 5, and then I have to skip past it, and then I have to look at 9 and so on. So I have to go through the entire list for a given vertex to determine whether or not there is an edge. So it's a little bit more expensive. On the other hand, if I want to know all the neighbors of I, right, then the adjacency list directly gives it to us. Right? So if there are 5 neighbors, there are 5 entries. Anyway, I have to look at 5 entries, I will find them. If there are 2 neighbors, I'll get 2 entries. On the other hand, in an adjacency matrix, regardless of how many real neighbors there are, you have to scan the entire row because you don't know whether there is a 1 coming up or not. So you can't stop and say, okay, after 7, I don't believe there are any more neighbors, right? So you have to go, for example, if you start at 8, I cannot go up to this point and say, okay, I have found 1 neighbor and there are no more. You have to keep going because you might find a neighbor at the last position. So regardless of what is the actual degree or out degree in this case, because it's a directed graph, regardless of the actual degree of the vertex, you have to spend order n time in order to collect all the neighbors of a given node, whereas in an adjacency list, the time you take at each node is actually proportional to the degree. Now in practice, many graphs will have small degree. A given node will not be connected to very many other nodes. So therefore, if you have a procedure which is proportional to degree rather than to number of nodes, it often works much faster. That's why it's useful to have this representation. So there are trade-offs, right? So it's not always the case that one is better than the other. So typically an adjacency list will save space, but there are some situations where it will incur some additional computation and vice versa. Right? So if you can make do with an adjacency matrix, then it's very simple to work with it, but then you have to do the scanning of rows and columns. On the other hand, with adjacency lists, some things are not so convenient. For example, imagine how you would find out whether there's an incoming edge in a directed graph, right? Because an incoming edge will be recorded in the list for the other one. So you have to go there and look at that list. Right? So there are other things that you have to do indirectly with an adjacency list representation, but it's important to recognize that there are these two different ways of representing graphs, and both of them are used in algorithms. So to summarize, what we have seen is that we can't just think of a graph as a picture to describe a procedure on it. We need a representation. Right? We need a way of writing it down in a way that we can manipulate mathematically. And we came up with two different representations. So one is this adjacency matrix, which is a matrix of n cross n for n vertices, which says that aij is 1 if there is an edge from I to j, otherwise it's 0. And the other one, which is more compact in general, if we have not very many edges, is what's called adjacency list, where for each vertex we list out the neighbors of that vertex in a list. And with either one of them, we did an example using the adjacency matrix. You can do now systematic computation. So we did this systematic exploration of whether or not a vertex V is reachable from a vertex view. So we will look at more such things. In particular, we will look at these two strategies which we mentioned but did not do in detail, which is breadth first search and depth first search. And then we will also look at other properties of graphs that you can compute using these two representations.